Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to gravitation and gravity. So in this video we are going to discuss about the experimental determination of the value of gravitational constant. So far we have discussed the basic concepts related to gravitation, that is every body in the universe, it attracts every other body with a force called as the gravitational force. And when one of the attracting objects is Earth, then that gravitational force is called as gravity. We also discussed Newton's universal law of gravitation, in which we got the mathematical expression of the gravitational force, which is, suppose there are two bodies of masses m1 and m2, their centers are separated by a distance r, then the gravitational force of attraction which one exerts on the other, it is given by this expression, F is equal to g m1 m2 by r square, where the force is directly proportional to the product of the two masses, inversely proportional to the square of the distance between them. Okay, so we have F is equal to g m1 m2 by r square. So here the important thing is this, the gravitational constant. That is the important thing. So we, in the previous video we just discussed, we just said that the value of g, it is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg squared as per SI unit, and 6.67 into 10 to the power minus 8 Dine centimeter square per gram squared as per CGS. But how we got this value? So there is an experiment which was conducted by Henry Cavendish in 1798 to get an approximate value of the gravitational constant. It was called as the Cavendish experiment. So in this experiment, what he did is that he took two lead spheres, small sized identical lead spheres, each of mass, let's say small m. Okay, he connected them to the two ends of a light straight rod of a fixed length capital L, and he suspended that rod with the help of a vertical quartz fiber wire which is connected to a particular point. Then near to this small size spheres, lead spheres, at a fixed distance on either side, on the opposite side, he placed two large sized identical lead spheres, okay, of mass capital M. Okay, small size lead spheres of mass small m, large size lead spheres of mass capital M. So each of these pair of spheres, they are identical and they are placed at fixed distance from each other in opposite directions, fixed distance r. So as per the universal law of gravitation, each of these small spheres will get attracted towards the large spheres because of gravitational pull. Okay, it will get attracted and that gravitational force is F. So the magnitude of the force, it will be the same in both these cases, because in each of these two body system, the mass of the two bodies, it is fixed. Okay, the separation distance is fixed r. So the magnitude of the gravitational force with which these small spheres, they get attracted towards the large sphere, that will be the same. So the gravitational force will be the same, but the direction is opposite. Okay, it is in opposite direction. Okay, like this. So as a result of this, both of these gravitational forces, which are in equal magnitude but in opposite direction, it constitutes a couple. Okay, the value of the gravitational force is this, g capital M small m by r square. Okay, as they are equal in magnitude but in opposite directions, they form a couple and it exerts a torque which is called as deflecting torque. It deflects the rod and the quartz fiber wire, it gets twisted. Okay, so when the deflecting torque, it causes the quartz fiber wire to twist, the restoring torque of the wire, it tries to bring it back to the initial position for rotational equilibrium. Okay, so here the restoring, it happens until both the deflecting torque and the restoring torque in the opposite direction, it becomes equal. Okay, so the deflecting torque is given by force multiplied with length. Okay, here either force multiplied with the length from the point, okay, that is F into L. Now F is the gravitational force, which is equal to gmm by r square. Okay, the gravitational force between these two masses in this two body system. The small lead sphere, it gets attracted towards the large lead sphere by this much amount of gravitational force. Okay, the value g capital M small m by r square, and the deflecting torque, which is F into the length of the rod. Okay, the force multiplied with the length, that is equal to g mm by r square L. Okay, the restoring torque of the quartz fiber wire, this quartz fiber wire, that is equal to k theta, where k is the torsion constant of the wire. It comes with the specification sheet. Whenever you are using a particular wire for experimental purpose, the torsion constant of that wire is given. Now all we have to do is to measure the angle of deflection. It is used by using a light and mirror arrangement. The angle of deflection is measured. Okay, how much amount the ray of light gets deflected. So we get the value of theta. Here we have small large M, capital M, R and L, we know. Okay, we have fixed the length of the rod is fixed, we know it. The mass of the larger sphere, we know it. The mass of the smaller sphere, that we know. The separation distance also we know. The torsion constant we know, and the angle of deflection, that is measured with a light beam and mirror arrangement. Now we know for rotational equilibrium, both the deflecting torque acting in one direction and the restoring torque of the fiber wire acting in the opposite direction, they should be equal. Okay, they should be equal in magnitude but opposite in direction, opposite in nature. So deflecting torque is equal to restoring torque. So gmm by r square L is equal to k theta. So here g is equal to k theta r square by capital M small m capital L. Now here we know the value of torsion constant of the wire. It is given in the specification sheet of the wire for the experimental setup. Theta is to be measured by using a light beam and plane mirror arrangement or any normal mirror arrangement. Then the separation distance we know. Okay, R, the separation distance between the larger sphere and the smaller sphere, it is known in the experimental setup. Then the mass of the larger sphere, that is also known. The mass of the smaller sphere, that is known. The length of the rod, that a light rod, the dumbbell rod, that is also known. So as all of these parameters are known, just we know the value of, we have to determine the value of the angle of deflection of the quartz fiber wire, the angle of deflection of the dumbbell rod. Then we get the value of, the approximate value of the universal gravitational constant. Okay, so as per this experiment, we calculated the value of G, which is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square, or 6.67 into 10 to the power minus 8 Dine centimeter square per gram square. Okay, so this is the experiment which was done. Again, the value is approximate. We can never get an accurate value, so this is the approximate value. Okay, so up to 2 decimal places here, 6.67. There are other values as well, but here for now we'll just stick to this much point. Okay, 6.67 into 10 to the power minus 11 Newton meter square per kg square, or 6.67 10 to the power minus 8 Dine centimeter square per gram square. So here every parameter is kept fixed. The length of the rod, the mass of the small size spheres, the mass of the large size spheres, then the torsion constant of the wire, everything was kept, it was controlled by the person who was conducting the experiment, the known parameters. The only unknown parameter was the angle of twist or the angle of deflection theta. It is measured by using a very simple light beam and plane mirror arrangement. So by measuring the angle of deflection of the reflected ray and the transmitted ray, we can get the angle, the twisting angle or the angle of deflection of the rod, and once we get that value, theta will also be known. So the remaining values are controlled by the person who is conducting the experiment. Only theta is calculated, then by using these known values we get the value of capital G, okay, which is the universal gravitational constant. This, okay. So all the quantities on the right hand side, they are known, so we get the value of capital G. So this is the experimental setup for determination of the value of universal gravitational constant, okay. So this is the thing.